In this problem, the AK is psi square k divided by k to the power 7 over 2. Note that the sign of the k is bounded by the value negative 1 and positive 1. When you square psi value, the psi square is bounded by the value 0 and positive 1 because the negative psi raised to the second gonna become positive number. That means this AK term is less than or equal to 1 over k to the power 7 over 2. It's convenient to set up the inequality for the direct comparison test. Since the limit of the psi gonna be doesn't exist, so the limit comparison test is not working for this problem. We're gonna compare with the p series, the sigma notation 1 over k to the power 7 over 2. P equals 7 over 2, which is greater than 1. We know this series converges. To compare with the convergent series, the BK on the right hand side greater than or equal to the AK, which is on the left hand side term. We're going to set up the inequality to be true for K greater than or equal to 1. AK, which is psi square K, divided by K to the power 7 over 2, less than or equal to, assume the BK right now is 1 over K to the power 7 over 2. Is that true? Yes, it is true because the psi is bounded by the value 1. Sorry, psi square is bounded by the value 1. It's true for K greater than or equal to 1. Then by the direct comparison test, this series converges. But the limit, as I mentioned earlier, the limit comparison test doesn't exist because the limit, the AK over BK as k approaches infinity equals the limit of the psi square k over k to the power 7 half multiplied by the reciprocal of the bk, or k to the 7 over 2 over 1. K approaches infinity. This limit doesn't exist. So the limit comparison test is not, um, is inconclusive. Another example, ak equals to k squared plus 3 divided by k square root of k to the 6 minus k plus 5. Consider the term of the ak as k approaches infinity. The leading term of the numerator is 2k squared. The leading term of the denominator is k times square root of k to the 6. Simplify this to be 2k squared divided by k to the power 1 times k to the power 3, which is k to the 4th. Simplify one more time to get 2 over k to the 2nd. We are going to use the p series with the bk as 2 over k to the 2nd, or p equals 2 greater than 1. We say this series converges. To compare with the convergent series, for this case, we have multiple terms on both numerator and denominator. It's more convenient to show by using the limit comparison test, or the limit of the AK divided by BK. K approaches infinity. The AK, or the term 2k to the 2nd plus 3 divided by k square root k to the 6 minus k plus 5 multiplied by the reciprocal of the bk, or k squared over 2. Take the limit as k approaches infinity. Again, we consider the leading term, then the limit value approaches to the value 1, which is less than infinity. Therefore, by the limit comparison test, this series converges, or both AK and BK series converge. Another example, AK equals 9 over K times square root of K minus 5. As K approaches infinity, this AK approaches to the term numerator 9, denominator K square root K, or 9 over K to the power 1 plus 1 half or 3 halves. Compare with the P series where P equals 3 over 2, which is greater than 1. We know that the series BK or the P series converges by the P series theorem. You either use the direct comparison test or the limit comparison test, but the limit comparison test is much more convenient. So find the limit of the AK over BK as K approaches infinity, or the limit of 9 over K square root of K minus 5 multiplied by the reciprocal of the BK, which is K to the power 3 half divided by 9. K approaches infinity. K to the 3 halves, which is the same as K square root K. The limit value of the L equals 1, or the number less than infinity. Therefore, by the limit comparison test, both series AK and BK converge. Or we just say the series summation AK converges.